Okay, so the next speaker is Oliver Edtmair from Berkeley, and we'll talk about the local strong Viterbo conjecture.
Well, thanks a lot for organizing this conference and also for inviting me to speak here. Right, so we'll talk about the local strong Viterbo conjecture. And this is all based on joint work in progress with Alberto Abundandolo and Gabriele Benedetti. Okay, so let me begin by recalling some basic concepts that are going to be important in this talk. So for me, symplectic capacity is going to be a function C that inputs some subset of R to n and outputs some non-negative real number or possibly plus infinity. And it has to satisfy two properties such that it's monotonic. So this means that if we take any symplectomorphism of R to n and any two subsets A and B of R to n, then if the image of A under phi is contained in B, then this should imply that the capacity of A is less than or equal to the capacity of B. And what this is saying is that this function can be used as an obstruction to symplectic embeddings, meaning that if the capacity of B was less than the capacity of A, then this embedding didn't exist, which is a very interesting statement. Right, and the second property is that the symplectic capacity should be like a two-dimensional quantity, and the way I want to state that is that it has a scaling property, which is saying that the capacity of R times, if it's scaled set by some positive real number R, I'm just getting R squared times the capacity of the set A. Right, so sometimes it's called an extrinsic capacity because we're talking about subsets of R to n, but for my talk, that's going to be a capacity. Okay, and so there's many examples of these capacities. Let's give some examples. The first, and maybe a trivial one, is just the volume of the set A. So that's clearly has this monotonicity property because a symplectomorphism preserves volume. It doesn't quite have the right scaling yet, but I can simply take the nth root of the volume, and then I would have a capacity that satisfies these two properties. Okay, but luckily there's many more kind of interesting capacities. And two capacities which I'm going to need in my talk is, first of all, the ball capacity. So that's sometimes also called the Gromov width in the literature. So this number, Cp of A, is defined to be essentially the size of the biggest ball that symplectically embeds into A. So I take the supremum over all positive numbers A, such that the ball, 2n-dimensional ball of symplectic width A, has a symplectic embedding into the set A. So that's a capacity. And then there's a similar one, which is called the cylinder capacity. Sometimes denoted by C set of A, and that measures the size of the smallest cylinder that the set A embeds into. So there's a infimum over all positive numbers A, such that A has a symplectic embedding into the cylinder of symplectic with A. Okay, that's two nice capacities. In practice, they're kind of useless because I can never compute them unless I understand symplectic embeddings, and that's maybe what I'm trying to use my capacities for in the first place. But the good thing is there's many other ways of defining these capacities that don't reference symplectic embeddings. So for example, there's what is called the displacement energy. energy E, which is based on Hofer geometry. So there I measure the smallest Hofer energy of a Hamiltonian diffeomorphism that displaces my set from itself. There's, for example, there's the Lagrangian capacity. Which measures the biggest size of a Lagrangian that can be embedded into my set. And then there's an important class of capacities that are based on dynamics. So there's a long list of these capacities, dynamical capacities. So an example would be, for example, the Hofer-Sender capacity or the equivalent Hofer capacities. And those actually come in a whole family that are parameterized by positive integers. There's what is called Good-Hutchings capacities or ECH capacities and, well, maybe even more. So there's a long list of these capacities. And there the idea is that if I input, say, a star-shaped domain in the capacity, then it has this rape flow on the boundary. And these are all kind of very sophisticated ways of extracting the action of certain special rape orbits on these boundaries. Okay, but so the thing I really want to say here is that there's a whole lot of different capacities, and the constructions kind of are very different, right? There's symplectic embeddings, Hofer geometry, Lagrangians, dynamics. So there's a big list of different constructions of capacities. Okay, so I will need something that's a bit more special. So sometimes one wants to normalize capacity, and for me, a capacity C is called normalized if the value on the ball of width A is equal to the value on the cylinder of width A, and it's also equal to A. And so not all of these capacities are normalized, but many of them are. So there's still a long list of these normalized capacities with very different definitions. Okay, and so there's a very interesting conjecture about these normalized capacities, which is in the literature often called the strong Viterbo conjecture. And this conjecture is saying that all normalized capacities agree on convex domains in R2N. Right? So we have the big class of all convex domains in R2N, and then a long list of different ways of defining a normalized capacity, and then the conjecture is that all of these things should just be the same number. So that's a very interesting conjecture. So let me remark that actually this conjecture is equivalent to just requiring that the ball capacity is equal to the cylinder capacity on all convex domains. So the reason is that any other normalized capacity, essentially almost by definition, is kind of squeezed between these two anyway. And so if these two agree, then all of them have to agree. Right, so that's this conjecture. It's called strong Viterbo conjecture in the literature. It's not quite clear whether Viterbo actually wrote this conjecture down. But the reason it's called that is that it implies the conjecture that Viterbo actually did write down. So let me call that just a normal Viterbo conjecture. So this one is saying that if C is normalized and if X is a convex domain inside a Euclidean space, then we have this inequality that's saying that the capacity of X to the power of n over n factorial times the volume of X is less than or equal to 1 with equality if and only if the X actually is symplectomorphic to a ball. Right, so this you can think of some sort of isobarometric inequality. So instead of trying to find the domain with the smallest surface area, of a given volume. Here we try to find the domain of the biggest capacity with a fixed volume. And the conjecture is that this is optimized exactly by those domains that are symplectomorphic to balls. Right, and for the ball, we know that we have equality here, and then it's conjecture that it's like this. So maybe I should remark that this conjecture doesn't quite imply this full statement. So it implies this first inequality, simply because this inequality is true for the ball capacity simply by the volume obstruction. And then if all capacities agree, then it must be true for all normalized capacities. The second part, it's not quite clear how it immediately follows from this conjecture, but at least the first one does, and that's maybe the reason for this terminology here. Okay, so there's also an even slightly weaker version of this. So that's maybe a remark. So for C equal to, let's say, the Hofer-Sender capacity, which is known to be just the action of the systole on convex domains, for this special capacity, this conjecture is in the literature also sometimes called the VIII. Viterbo conjecture, even though Viterbo does not like to have VIII in front of his name, so I should point out that the VIII goes to the conjecture. Okay, so that's these three conjectures. And right, they're all very interesting, but of course kind of wide open in full generality. But there's been kind of a lot of work that tries to make partial progress towards these conjectures. And there's kind of one direction is to look at kind of local perturbative versions of these Viterbo conjectures. And the first result in this direction that I know of, so now I want to talk about local results. So the first theorem that I'm aware of is the result of Abbondandulo, Barney, Bramham, Umberto, and Pedro from, I think, around 2015. So this result is saying that the VIII Viterbo conjecture holds for convex domains X inside R4, so we are in dimension 4 here, that are C3 close to the ball. Right, so we have the ball, and everything that's C3, sufficiently C3 close to the ball satisfies this VIII Viterbo conjecture if we are in dimension 4. Right, and that's a pretty cool result, and it has kind of inspired a whole lot of follow-up work. So just to give some examples, there's an extension of this due to, well, again, Abbondandulo and Gabriele Benedetti, 2019, and that's saying that the same actually works in arbitrary dimension. Right, and yeah, there's even some more work in this direction, and I think we'll learn about this tomorrow from Marco. So here, so yes, the ball, the rate flow in the boundary of the ball is what is called the sole rate flow, in that all the rate orbits are closed to the same minimal action. There's a more general thing called the Besse rate flow, where all the orbits are closed but might not have the same action. And then you can try to look at perturbative results near Besse rate flows, and we'll hear about that tomorrow. Right, so there's these results. And then last year, I proved something as well. So I proved that in the four-dimensional case, so there's the strong Viterbo conjecture holds in this perturbative setting. So the strong Viterbo, so that terminology he actually likes, he said, holds for X in 4-dimensional space, C3 close to the ball. Right, so we can go from the weak to the strong one in dimension 4. And then in view of this result here, it's very natural to ask, can you kind of combine these two works and get the thing in arbitrary dimension? And that's the main result of today. So the result is that, so that's joined with everyone down below and Benedetti, myself, that actually the same here holds an arbitrary dimension. Same in arbitrary R to n. Okay, that's the main result I want to talk about today. So then maybe let me say something about the C3 here. So as far as local results are concerned, maybe the most natural thing to look for is the C2 topology. So we're looking at convex domains, and if I want a perturbation of the ball still to be convex, then C2 small is the right thing to ask for. So the C3 is slightly worse. We can't quite get to C2 yet. We can do a bit better than C3, but then it's maybe getting a bit too technical for now, so I will leave it at C3 here. But C2 would be the ultimate goal, but we can't quite get there yet. Okay, so right. Let me briefly mention kind of a byproduct of our result here that kind of connects very well to Marco's talk, I think tomorrow. So for that, it's kind of a byproduct, which might be interesting in itself. So we have this notion of a normalized capacity here. One can also look at different sorts of normalizations. And one thing one could introduce if one wanted to is the following notion. So a capacity C is called K normalized, where K is some positive integer. If the capacity of E equals the kth equivalent Hofer capacity of E, whereas E ranges over all ellipsoids in our dimension for all ellipsoids. So we have this sequence of capacities, the equivalent Hofer capacities, and one could require that our given capacity should agree with that on all ellipsoids. And right, so with this definition, I can remark that normalized, in this sense here, turns out to be the same as one normalized. Normalized is equivalent to one normalized. So we can view this as an extension of this definition. And then something we can prove is that theorem that all n normalized capacities agree on X inside Euclidean space. So here there's an n here, which is exactly the n that shows up here. So it's like the n that's half the dimension on all these X that are C3 close to the ball. Right, and so I don't really want to say that much more about this result, but it's kind of going to become relevant in Marco's talk, where I will hear more about these higher normalized capacities. Right, so one can, maybe one wanted to conjecture or ask, do all n-normalized capacities agree on all convex domains? So it would maybe be the generalized strong Viterbo conjecture. Yeah, but I guess we will hear more about that tomorrow. Okay, so yeah, I want to now talk more about this result here. And so unfortunately, like the proofs of all these results are kind of technically very complicated. So it's kind of, just looking at the proof is maybe not quite clear what happens, but I hope I can kind of explain some of the main ideas here in terms of a very classical topic. So in the 90s, there was work on geodesics on the Hamiltonian diffeomorphism groups with respect to the Hofer metric. And so that's work of Bialy and Batoreo and McDuff-Lalande. And it turns out that one can kind of interpret what's happening here in terms of just very classical theory, and maybe that illuminates a bit better what's really happening in all these local results. So that's the plan for today. I want to tell you how this connects to geodesics and the Hofer metric. Okay, and so for this purpose, so why we only get C3 close? Maybe we'll see a bit better later. But yeah, that's really at the heart of the technical difficulties. So we can do a bit better than C3 close, but remember the question and ask it again later. Or just forget and maybe I can get around. Right. Okay, so I want to now introduce the notion of a contact Banach-Mesur distance. So that for that we fix a closed contact manifold y2n minus 1 with some contact structure xi. I mean, for the purpose of this result, the relevant contact manifold is just a sphere of the standard contact structure, but this story works kind of in general. So we fix this, and I want to call lambda the set of all one forms on Y, which actually are contact forms for a fixed contact structure xi. So that's this set of these contact forms. And on this set, I want to define a pseudo distance that could be called the contact Banach-Mesur pseudo distance. So I define a pseudo metric on this lambda by setting the distance of two contact forms alpha and beta to be equal to the infimum of the following quantity. We have the maximum of f minus the minimum of f, where the following is true. There exists a contactomorphism phi. So look at cont 0, that's all contactomorphisms that can be connected to an identity through contactomorphisms of this contact manifold, such that phi pullback of alpha equals to e to the power of f times beta. Right, so we look at all these contactomorphisms, we pull back our alpha. It's a contactomorphism, so it's the same contact structure, so we get a contact form that's just a scaling of beta. There's some unique function f that goes here, and here we just take the maximum of f minus the minimum of f. And then that's a number, and this is the pseudometric. So some comments about that. So this thing is actually invariant under a certain group action. So we have an action on lambda of this group R cross cont 0, where the action is given by alpha is acted on by s comma phi by e to the power of s times phi pullback alpha, right? So we can pull back contact forms and we can just scale them. So we have this kind of group action, and actually the pseudo distance is invariant in that. So if we replace alpha by anything in the orbit of alpha, we get the same distance. So really what this is doing is it looks at alpha and looks at beta, and it looks at the orbits of alpha and beta under this group action, and it takes some sort of C0 distance of that. So that's what's happening. So if one wants to draw a picture, one could do it as follows. So the picture would be that we consider the symplectization. And in the symplectization, so that's kind of R across the contact manifold. So first of all, like any contact form really is going to be a hypersurface in symplectization. So we have one hypersurface, which is the one that corresponds to the contact form beta. And then there will be some other one that corresponds to the contact form alpha, right? And then we kind of, then there's some C0 distance. So then we are allowed to modify alpha by pullbacks under phis. So we can try to pull back alpha under some phi and get some new hypersurface here. That would be the one that corresponds to phi pullback alpha. And on the other hand, we can take this hypersurface corresponding to beta and kind of translate it up and down. So we could translate it like this and translate it like this, right? So such that this one is squeezed between the two translates. And really what we're doing is we're trying to minimize this distance here. So that's what this formula is saying. So you can kind of translate this one up and down, and you can pull back this one, and then you try to squeeze as tight as possible. So that's this quantity. Right, it has some kind of versions of this kind of pseudometric have been introduced before in like the last couple of years. So there's a version of this, so maybe not quite the same, but very similar. Similar pseudo metrics due to this work of Rose and Zhang. There's also work of Melistas, and then there's a version of this not for contact forms but for kind of symplectic domains that I think was first proposed by Ostrova and Batoreo, and then kind of further explored by some other people. Right, so this kind of notion has kind of been studied in the recent years, and then most of these works kind of focus on the large scale geometry of this kind of pseudometric. So I would be asking questions like, is the diameter of this thing infinite with respect to this pseudometric? Things like that. In my talk, I kind of want to go in the opposite direction, and I want to focus on maybe the small scale geometry. Okay, in particular, the question we will be interested in is the following. So the important question for these kind of local results here is the question of when is the infimum in the definition of this pseudometric D attained. Right? So we fix two contact forms, then there's some infimum, and it can happen that the infimum actually is attained by some choice of phi and f, and sometimes maybe not, and we're interested in when does it happen and what does that mean. So it turns out that that's the important question to ask here. Right, and the reason is the following theorem. Maybe we'll go over there. reason is the next result. So this one is saying the following. So let's assume that the inf in this definition of d alpha beta for some choice of alpha and beta is attained. And so what this means by definition is that there exists a function f and a contact homomorphism phi such that the distance of alpha and beta is equal to the max of f minus the min of f and phi pullback alpha equals to e to the power of f beta. So let's assume this is the case. So in a picture, right, there would be, again, a symplectization, and then there would be some hypersurface that corresponds to phi pullback alpha. And then there's, on the one hand, we have e to the power of minimum of f times beta, and up here we have e to the power of maximum of f times beta. So that's two translates of beta, and then these two are going to touch in some non-empty closed sets. And this distance is exactly going to be this value here. So we assume we are in this situation. It's not at all clear whether it happens at all, but we assume that's the case. And then it turns out that two statements are true. So then the following happens. And so here's the more important one. So it turns out that there exists probability measures that are supported in, so one is supported in the set f inverse of max of f. So that's supposed to be this set up here, where this contact form touches this contact form here. So there's one probability measure supported in this set, and another one in, well, this set down here, where the contact form touches the lower one, and f inverse of min of f. And they're not just any probability measures. They're supposed to be invariant with respect to the rape flows of both the contact form phi pullback alpha and the contact form beta. Right? So the idea here is that, well, if you look at this set here, then this hypersurface corresponds to phi pullback alpha touches this hypersurface. So at all of these points, the rape vectors are going to be parallel, right? And similarly down here, so whenever these touch, then they are tangent, and the rape vector just needs the first derivative. So the rape vector fields are kind of parallel in these touching sets. And I require that, right, so we can conclude that these two subsets where the rape vector fields are parallel, in fact contain, support some invariant probability measures. That's the first statement. Maybe the more important one. The second one is we can also conclude, that there exists a minimizing geodesic in lambda from alpha to beta. Right? So at first it's not quite clear, like, do there exist any geodesics? And then here we say, well, if the infimum is attained, then we do have this connecting geodesic. Okay, but the more important one for this talk is going to be the first one, the existence of these probability measures. And in fact, it's maybe not quite the hardest thing to show. So somehow the idea is that right, if we assume that the infimum here is attained, then it kind of must be impossible to in any way push down this hypersurface any further, right? So if I try to push down the hypersurface, I could do that with maybe a Hamiltonian diffeomorphism of a symplectization. And if I kind of want to push it down everywhere where the hypersurface is touched, I need to have some sort of function or Hamiltonian whose derivative in the direction of the ray vector field is always positive along the set where they touch, right? Whenever I have such a function, I can push it down, and it's not going to be optimal. So I can come from the optimality from the infimum here attained conclude that this kind of function does not exist. And then there's a theorem that's called the Sullivan alternative that lets me conclude the existence of these invariant probability measures. Right. So it's saying that the infimum is attained, we have these common invariant measures. Okay, so now how does this help with the Viterbo conjecture? So the first observation one can make is the following. So it's an easy observation. We have the following. So remark. If one of my contact forms is a Sol contact form, so if beta is Sol, which means that all the flow lines of beta are closed of the same minimal period. So for example, if beta is the contact form on the boundary of a ball, then, well, in fact, e to the power of the minimum of f beta, and also e to the power of maximum of f beta, and this phi pullback alpha share a closed orbit. So the idea is we already know. So we assume that this infimum here is attained, and then we know they share a common invariant probability measure, but then the flow of this beta was Sol, and we conclude actually must have been an orbit. All right, and so a consequence of this is that the systolic ratios satisfy an inequality. So we have the minimal action of alpha to the power of n over the contract volume of alpha. That must then be less than or equal to the minimal action of beta to the power of n over the volume of beta. And this quantity is also called the systolic ratio, which is the one that shows up in the weak Viterbo conjecture. Right, so if we have this Sol contact form, it has some systolic ratio. And if you have any other contact form alpha such that this infimum here is attained, then the systolic ratio of alpha was at most the systolic ratio of beta. Right, so that's an immediate consequence. And yeah, one other thing we can kind of immediately see from this is, so it's known that, okay, so this quantity here, I want to call it the systolic ratio sus of alpha, and it's kind of known that that the systolic ratio is always unbounded. It's an unbounded function in the space of all contact forms. So in this generality, that's a result of Saglam, and in special cases for special contact manifolds, that was this work of Abondandolo, Pramham, Renewage, and Salomao. So in particular, if I have some contact manifold and which has some Sol contact form, I can immediately find contact forms where this infimum is not attained, simply because if it were attained, then we have this systolic inequality, but there's contact forms which have higher systolic ratio. Okay, so right, at this point, it's not at all clear yet that any of this is useful, because we always have this assumption if the infimum is attained, and we just learned it's not always attained, but at this point we don't even know, well, is it attained at all. And that's maybe the main result. of this whole story. So this result is saying that.
Could you repeat how you use solid and not Besser?
Well, maybe Besser is actually enough. Yeah, could be enough. Yeah, I just said solve because I was always thinking about solve things, but. Okay, so that's maybe the main result here. So that's the theorem. Maybe let's put it here. Theorem. So let alpha 0 be Sol. So we fix our favorite Sol contact form, and then if an alpha is C3 close to alpha 0, then it is true that the infimum in this distance of alpha to alpha 0 is attained, and moreover, it is also true that this distance of alpha and alpha 0 is actually equal to the logarithm of a quantity A max of alpha over A min of alpha. So what are these? A min of alpha really is the systole, the action of the shortest orbit of alpha. A max is the longest action of a short orbit. So the idea is we have this Sol contact form with all the orbits closed, and then we have like a small perturbation, and then the closed orbits of the perturbation kind of come in two classes. There's closed orbits of the perturbation that are just perturbations of the closed orbits of alpha 0. Like there's like a simple orbit here and slightly perturbed, and there's these kind of orbits. Those I want to call short orbits. So the action of these short orbits are close to the minimal action here. And then there are other orbits which are kind of perturbations of multiple covers of these orbits. So the action of those is kind of at least twice the minimal action here, or kind of a small perturbation of that. So that would be the long orbits. And then I can just take the longest action of a short orbit, and that's this A max quantity. Right? So I kind of look at just all the orbits that look very close to orbits here. That's the short orbits, and then I have this ratio, and actually this distance is, the infimum is attained, and we have this equality here. Okay. So we have interesting situations where the infimum is attained. Right, here we have, again, the C3 closeness. And, okay, so now I have this theorem, and then now I want to kind of state a very classical theorem in a very similar form, and that's then hopefully making clear, like giving an idea of what really is happening here. So that's the following theorem. Well, okay, so by the way, so I guess at this point, we can already recover this result here, right? So we had C3 closed to a solving, then this infimum is attained, and then we have this remark here. So we already can, just from the fact that the infimum is attained here, we can already recover this result, and of course also this one. Okay, that's a remark. But right, so now this old and classical result. So that's work of Bieli and Batoreo. It's from the 90s. And I'm kind of just stating it in the form that's most symmetric to this thing here, and not necessarily how they originally stated it. But what is true is that if a phi is a Hamiltonian diffeomorphism, let's say compactly supported of R to n, and if this thing is C1 close to the identity, then the infimum in this quantity dh of phi and the identity. So this is the Hofer distance of phi to identity. This definition also requires an infimum. So this infimum is attained. So here the infimum is taken over all time-dependent Hamiltonians whose time 1 map is this phi, and for every Hamiltonian I have the Hofer energy of the Hamiltonian. So there's this infimum, and this is saying if we have something that C1 goes to identity, then there's a Hamiltonian which achieves this infimum. So that's true. And moreover, this dh of phi and identity actually is just equal to a max of phi minus a min of phi. So what are these two quantities? So phi is going to have fixed points. Every fixed point is going to have an action. There's different ways of defining that. For example, one could take a generating function and just look at the value at the fixed point. I could take the maximal action and the minimal action, and I take this difference. It turns out that's exactly equal to the Hofer distance. Right, so this is a very classical result. And right, that's for R2n. There's work of McDuff and Lalonde that works for more general symplectic manifolds. Right, another thing I can conclude here that there is a minimizing geodesic from the identity to phi, simply generated by this Hamiltonian that is achieving the infimum here. Right, so if this result, and I on purpose stated it in this form, so it looks very similar to this result. So really I want to view this thing here as the contact version of this result here. So somehow these contact forms really correspond to Hamiltonians, and then they get infimum of Hamiltonians, and here really there's an infimum over these kind of deformations of the contact form by contact homomorphisms. So there's two very similar kind of distances. It's like both have very this kind of C0 flavor, and we have these results. Right. So maybe the only annoying difference is that so here we have C1 close, which somehow corresponds to C2 small Hamiltonians, right? So the Hamiltonian, for the Hamiltonian vector field, I lose one derivative. So this kind of looks like a C2 small Hamiltonian. And now here I have C3 small, so that's annoying. So really I would want to get C2 here as well, just as in the Viterbo conjecture. We can't quite get there. So the thing we can get, and maybe that's answering a little bit the question is, so we can do the following. So in this theorem here, so remark, let's call that theorem star. So in star, we can make the following assumption. We can say for every d bigger than 0, there exists a delta bigger than 0, such that for all contact form alpha, such that alpha minus alpha 0, C3 is less than d, and alpha minus alpha 0, C2 is less than delta. If this holds, so then this d of alpha and alpha 0 is achieved. So this is saying that I can fix an arbitrarily large d, right? And then I look at the C3 ball with this radius d, right? And then given the d, I can find a delta such that I can intersect with the C2 ball, that's a small delta, and then this whole statement, the assertion here, holds for all these contact forms. The problem is that a delta could become very small as the d becomes big. So it's not quite C3, but it's kind of close. And yeah, it's not quite clear whether that's just a technical thing or whether we can remove it. But yeah, as I said, many of these things are kind of a little more subtle than for Hamiltonian diffeomorphisms, maybe similar to Victor's talk in the morning. So some things become a bit harder. Okay, so I have 10 more minutes. So the first thing I want to do is, I want to explain how to get, how how to get from this theorem here to actually this main theorem. So I already argued that we can get the local weak Viterbo conjecture. Now we want a strong one. Okay. Okay, so now I want to actually give a proof. Proof of theorem, that's theorem A. Okay, and I kind of want to deduce it from this theorem star here. Okay, so we take an x inside R to n, that's C3 close to the ball. Right, we start with that, and the thing we want to show that the ball capacity of x actually agrees with the cylindrical capacity, and then because any other capacity, normalized capacity, is squeezed between the two, we get the statement we want. And okay, there's kind of two steps to this equality. So the first step is kind of the easier one, is to show that the cylindrical capacity under these assumptions is actually less than or equal to the action of the systole of the wave flow on the boundary of x. So that's actually not that hard to show, and it already, I think it was shown in this work here. So somehow the idea is that the systole under this C3 closeness assumption is going to be just a small perturbation of a Hopf fiber on the boundary of the ball, right? So then I can have look at an ambient symplectomorphism of R to n that takes the systole of x and moves it actually into a complex line. It moves it to an actual just Hopf fiber, and it's going to deform this domain x somehow. But because the systole was very close to the Hopf orbit, this Hopf fiber, I can choose my symplectomorphism, I don't know, maybe C2 close to identity, right? So then this symplectomorphism is going to preserve the convexity of x. And once I have a convex domain where the systole is in a complex line, it's not hard to see by convexity that it's actually contained in the right cylinder. So that's this argument here. So that's kind of the easy part. The hard part is, the second step, is to show that the ball capacity of x is actually bigger than or equal to the systole. Right? Once we can show that, then we can conclude everything. And then how do we do that? So the first thing I want to do is, so here we have these star-shaped domains. Here we have contact forms. And these kind of correspond to each other. So I will identify R to n without the origin. I can just regard that as the symplectization of the standard contact structure on the sphere. So the picture here is where I have the origin, I take it out, and I have the sphere, and this R to n, I can just view it as the symplectization with like the positive end at infinity and the negative end concentrated at the origin. And in this identification, then these boundaries of star-shaped domains exactly correspond to these hypersurfaces in the symplectization and therefore to contact forms. Right, and so in particular, right, I have my x and I have my ball. So this B is the ball, that's the domain I started with. And then they're going to correspond to a contact form alpha and a contact form alpha 0. This alpha 0 is Sol because the wave flow on the boundary of the ball is Sol. And then this thing is C3 close to the ball, so these two things are also going to be C3 close to each other, which means that we are in a position to apply this theorem here. And I will erase everything above that. want to now apply the theorem star. And from that, we can conclude that well, we can find this phi and an f such that phi pullback alpha is e to the f alpha 0. The max of f minus the min of f is just our contact Banach-Meser distance. Right, I can find these two things by this theorem. And then, well, we had the theorem that I think was here. No, this theorem about the common invariant measures, that in the case of one of them being a sole contact form actually are just orbits. So from this we can conclude that, so this other theorem, we can conclude that our phi pullback alpha and e to the power of the minimum of f alpha 0, they share a common closed orbit. Okay, and so then we have this contact form here, and that's again going to correspond to some star-shaped domain x prime, right? And then this contact form, that's a Sol contact form, so it's going to correspond to some ball of some width, and this width A is bigger than or equal to a min of x, simply because right, these two things share an orbit. So the minimal the action of the systole of x is the action of the systole of this thing here. It can only be less than or equal to the width of this ball, right? Because this ball and this x prime share an orbit. So we have this inequality. So that was the statement about the common invariant probability measures. And now we are essentially almost done. I guess this is not meaningful anymore. So now we're almost done. So we certainly have that x minus the origin is symplectomorphic to x prime minus the origin, right? So the x was corresponding to the alpha. The x prime was corresponding to phi pullback of alpha. That's a conjecture. I can kind of lift it to a symplectomorphism of the symplectization. So it lifts to a symplectomorphism of the complement of the origin, right? A very annoying thing is that in higher dimension, I cannot conclude that x is symplectomorphic to x prime. So in dimension 4, that's a result of Gromov-Mekdaf that uses pseudo-homomorphic foliations that lets us conclude this. In higher dimension, we don't know. But it turns out we don't need to know. So we can simply do the following now. So we have the ball capacity of x, and actually that's just equal to the ball capacity of x minus the origin. So why is that? So the idea here is that the symplectomorphisms support inside x. They kind of act transitively on the interior. So we can just think of this origin to be arbitrarily close to the boundary. And then the ball capacity agree because it simply was a supremum over the size of balls. Right, so we have this. Then we have a symplectomorphism here. So that's the ball capacity of x prime minus the origin. Then the same reasoning says that's the ball capacity of x prime, right? But so now, kind of here, the x prime just straight up contained this ball because this contact form was strictly below this contact form. So because, right, so that's bigger than or equal to a, simply because B of A is just contained inside x prime. And I said here that the A was bigger than or equal to the A min. Right, equal to A min of x, and then I'm good. Okay, so that's how this theorem here kind of not only rather easily implies the local weak Viterbo conjecture, but also the local strong Viterbo conjecture. Okay, so the time is out as well. So that's good. So we have this classical theorem. We have a contract version of it, and it implies these local Viterbo results. That's nice. So I didn't really say how to prove this thing, and that's really where it becomes very technical. So somehow, in this case, things are a bit easier, and so an important part of this is if we have this phi, we want to generate it by what's called a quasi-autonomous Hamiltonian. It's kind of one that kind of always attains its maximum at the maximum fixed point and always attains its minimum at the minimum fixed point. And to find such a quasi-autonomous Hamiltonian, really there's an argument that uses generating functions in the Hamilton-Jacobi equation. So it's like not that hard. That's kind of the thing that, at least at this point, it's like very technical here. So we do have some sort of normal form where we start with a contract form and we bring it to what we call a quasi-invariant form. Where invariant, so there's like this S1 action from the Sol rate flow. So there's this quasi-invariant normal form that somehow corresponds to a quasi-autonomous Hamiltonian. And then from there, one will kind of get this theorem. But yeah, that's a bit of a technical story, and I'm going to stop. I'm going to stop here. Right, thank you for listening.